Welcome back to our series of videos in robotics, and I hope you enjoyed the previous video. We spoke about continuous time machines. We looked at how to calibrate light sensors and why we need to calibrate them, and we also looked at the advantage of the calibrated light sensor over the uncalibrated light sensor if you took time to compare the output of what you did from your previous video to that which we did when we had not calibrated a light sensor. In this session, I want us to revisit our finite state machines. The first finite state machine we built was to build a robot or program a robot to move forward or backwards depending on whether a touch sensor was pressed or not. In this video, we'll take finite state machines a step further. Here, we want to implement a finite state machine for this same robot to perform the action we saw in the continuous time machine. So, a finite state machine for this robot to follow the black line on this white graph. Now, we start with the two states, which means we will have two possible actions for our machine to take depending on what is happening or values coming from a light sensor. With our calibrated light sensor now, we have values coming out, and we know that after calibration, we have opened up the range, so our values are ranging from 0 to 100. Now, just like any machine or any human being, our actions are dependent on our sensors. So our sensors are the first points or input into our system. So if these values are fed into our system, what can our system use these values for? It will use them to decide on what actions to take. So for a two-state machine, let us decide, or let us agree on our two set of actions. Virtually, we have a robot which is supposed to follow this black line, and we are starting with our initial condition where the sensor is positioned exactly half on the black, half on the white. So if the range of values are from 0 to 100, then in this position we are expecting 50% reflection from the light sensor. While navigating, our robot can either veer off into the black line or veer off onto the white mat. So our robot has two possible errors: an error of veering into the black or an error of veering into the white. So if the robot deviates into the white, then our action, let's take, so this is our right, this is our left. Let's take that when our robot deviates into the white, then the action will be to turn left. And if our robot deviates into the black, our action will be to do what? To turn right. So this is what we want to implement. We have a robot positioned exactly half on black, half on white. And if it deviates into the black, the action is to turn right. And if it deviates into the white, the action is to turn left. So the two states are turning right and then turning left. So at any point in time, our machine will be performing one of these two actions. So how do we get this into programming? We have to come up with a mathematical model, a mathematical equation that can implement this decision of veering into white or veering into black. So can we say that if the light sensor values, that is, if the value that comes out of the light sensor is compared whether it is greater than or equal to the midpoint value 50, the result from this equation will either be a true or a false. A true means the value is above 50, which corresponds to a drift into the white, because white surfaces reflect more light. And then a false stands for a value less than 50, which means the robot is drifting into the black because the black will begin to absorb more of the light. So we have been able to come up with the implementation of knowing whether the robot is in the black or in the white with the greater than or equal to sign, resulting in one of these two states. So if this is the state, if it is true that we are in the white, then we can go on with our action of turn left. And then if the result is a false, we can go on with our action of what? Turn Right. That is our finite state machine. So we have light sensor values, calibrated light sensor values being compared to the midpoint value, and the result being a true or false, which leads us into turning right or turning left. That was simple. We'll implement that in programming. But before we move on to the programming side, let us try to make this better. If we try to run this robot, we are going to have this. So our light sensor will be here, and the robot will be taking this action, moving this way, because as it drifts, the robot will do at control, turn left, turn right, turn left, turn right, and as it moves, we call this the drunken sailor approach. But we can do something better. So let's try to improve the behavior of this robot by implementing a 5-state FSM. So this time we want to give our robot 5 sets of actions from which it will decide what to do. Let's look at this. So our calibrated light sensor again. Values coming out of the calibrated light sensor between the range of 0 and 100. So if that value is divided by 20, the result is either going to be 0 points, a figure up to 1 point, a figure up to 2, all the way to 5. So what we can do now is, if we take this figure and round it up, then this is what is going to happen. It means, depending on what value is coming out of the light sensor, if the value ranges from 0 to 20, then the result round up will end up as a 1. If the figure is between 21 to 40, divided by 20, round up, we are going to have the result being a 2, because everything from 0.1, 0.2, 0. will be round up to 1. Every figure from 1.1, 1.2, 1. anything will be round up to a 2. It goes on and on. So figures between 41 to 60, round up will go to 3. Figures between 61 to 80 will end up as 4, and figures between 81 to 100 will end up as what? At 5. It means this mathematical model, that is the value from the light sensor divided by 20 and round up, will end up as either 1, 2, 3, 4, or 5. We can use this result as control point to decide on one of 5 possible actions. So let us write our algorithm or our pseudocode for this. So we are saying that figure is round up, and the possible results are a 1, a 2, a 3, a 4, or a 5. Now, when we have a 1, what it means is that the figure that came out of the light sensor was between 0 and 20. And what does it stand for? Anything between a 0 and 20 means that the light sensor had moved so much into the black. It was almost completely in the black, because if it was a 0, it means we are totally in the black. And that means our drift into the black is so high that we need a sharp turn to our right. So this will correspond to, let's say, sharp turn to our right. And how will I implement this? If I had this robot with this motor on port A and that motor on port D, then to take a sharp turn to my right, okay, so our robot is moving this way. To turn to my right, we have the motor on D has to be moving while the motor on A stops. So I will say the action will be stop motor A, and then move motor D. If I had a 2, it means the figure that came out of the line sensor was between 21 to 40, which meant that the robot was drifting into the black, but it was not so much in the black. So I may have to turn to the right, but not as sharp as I was turning here. So I will say slight turn to the right. And I can implement that by, let's say, I will slow motor A and then move motor D. So you see here we stop motor A and move motor D, which gives us a sharp turn. Here we only slow motor A while we move motor D. That gives me a turn to the right, but this time a more gorgeous turn. Then when I have a figure of 3 coming out of this equation, what it means is that I received a value between 41 to 60. Which would mean that my line sensor was almost at the desired position because the make value of 50 falls within the range. So I could even decide to say that at this point my robot should move straight. Because it could be that my robot was on a car like this. So it should move straight. So to move straight, I'll say move motor A and then move motor D. Whenever I put a move, I'm assuming they are moving at the same speed. And whenever I say slow, I'm assuming it is slowing down, or the slowed motor is moving slower than the move motor. So at the point, if I had a figure of 4 coming out, then it means I recorded values between 61 and then 80, which would mean that the robot had drifted into the white, but not so much into the white. So I could say again a slight turn, but this time to the left. So a slight turn toward the left. And that would mean I would move motor A and slow motor D. And finally, if I have a 5 coming out, it means I recorded values between 81 and 100. And values between 81 and 100 means the robot was totally almost drifting fully into the white. So I need a sharp turn this time to my left. So I'll say a sharp turn to the left. And how do I implement that? Instead of stopping motor A, so a reverse of this time I move motor A and stop motor D. So here I move motor A and stop motor D. So here we have a 5-state finite state machine, or a 5-state FSM. It gives us a more gorgeous navigation because we have more control. So you can go ahead and implement a 10-state FSM, a 20-state FSM. What you are doing here is taking analog values, which are a continuous range of values, infinite number of values. You are using division and then rounding up or rounding down. You could use any of them. You are digitizing the values into discrete values. So this is a finite state machine. You have finite set of actions that the robot can decide on, and you are free to decide on how many states you will have. With this, I think you should be able to implement any kind of FSM, and I believe you have learned a lot from this session. In our next session, we'll be programming a 2-state FSM to follow or navigate around this tile. We may add some other tiles. Then we will implement a 5-state FSM to do the same task. We can then compare and see that clearly a 5-state FSM gives us a more gorgeous navigation as compared to a 2-state FSM. Your guess is as good as mine. A 10-state will do better, a 20-state will do better. Or you could decide to handle every value by moving from FSMs and getting into continuous time machines. I hope you enjoyed this video. If you have any questions, leave them as comments. We will do well to address all your questions. Thank you for watching our video. Subscribe to our channel. This is part of the Robotics Inspired Science Education Program run by the Ghana Robotics Academy Foundation. My name is Michael Wilson. I work with the Council for Scientific and Industrial Research, and I am the Chief Trainer for the Ghana Robotics Academy Foundation. I also run the Microbot Academy. Subscribe to our channel, and anytime we upload videos, you will be notified. Thank you.